So we're going to continue our look at line spectra. We're going to try and put a bit more maths in this time. And the maths is really just the maths we used in the photoelectric effect applied to a new situation. Possibly the most confusing thing here is that we're going to give these energy levels, which we discussed in the previous video, we're going to give them negative numbers. This top line here, this dotted line, I'm going to call the ionization level. So if an electron manages to reach here or beyond, it completely leaves the atom and we've caused an ionization, as we discussed in the previous video. And by convention, when an electron is well separated from its atom, we say that it has energy 0. So all of these represent electrons with energy less than 0, and for better or worse, that means that all these energy levels will be labelled with minus energies. Now I'm just going to make some numbers up to make the point, but first of all, we use these integers to represent the energy levels. The lowest energy level is n equals 1, n equals 2, n equals 3, also called the ground state. That's important, and that's ordinarily where our electron will be if no excitation has occurred. We could label these in electron volts, and we'll do that in a future video, but I think we're just trying to keep it simple, so we're going to try and make these numbers fairly straightforward. So we're going to call the bottom one minus 5 times 10 to the minus 19 joules. I'm going to call this one minus 3.5 times 10 to the minus 19 joules. And we'll call this minus 2.5 times 10 to the minus 19 joules. So we're just trying to keep everything nice and straightforward for the moment, so we can kind of illustrate the point. So if an electron in the ground state has a collision with another electron, how much energy will be needed to move the electron to excite the electron from n equals 1 to n equals 3? Well, the difference between 5 and 2.5 is 2.5. So we need 2.5 times 10 to the minus 19 joules of kinetic energy to cause that excitation. So first of all, if this electron had got less kinetic energy than that, then this excitation couldn't occur. Assuming it's got enough energy, this electron is now going to proceed on its way and it's going to lose that much kinetic energy. So if it came along with energy 3.5 times 10 to the minus 19 joules, cause that excitation, and then it would have to go off with 2.5 times 10 to the minus 19 left. It would have that much energy. This electron is then sitting there, and realistically there are three things that can happen. It could fall all the way back down, and if it did that, the photon release would have to have energy 2.5 times 10 to the minus 19 joules, because that's the difference between these two energy levels. We should pause and have a think here about how we do the maths. I have my own preference, which is to ignore the minus signs and just say the difference between the magnitude of that number and the magnitude of that number is 2.5 times 10 to the minus 19. I know some students don't like that. So the way we should do it, if we want to do it strictly, is that the change is final minus initial. And you'll see why I don't like this. It's fair that I explain it, but it creates its own problem. So the final energy is minus 5 times 10 to the minus 19, minus the initial energy, which was minus 2.5 times 10 to the minus 19. Minus is plus. So minus 5 times 10 to the minus 19 minus 2.5 times 10 to the minus 19 is minus 2.5 times 10 to the minus 19 joules. So that's the change in energy of this electron. The energy it lost is the same as the energy gained by the photon. So the energy of the photon is 2.5 times 10 to the minus 19. So you've got to do a lot more work with directed numbers if you're going to do it the strict way. So which is why I tend to ignore it. Anyway, so we've got a photon. It's got energy 2.5 times 10 to the minus 19 joules. Let's have a go at working out what frequency that would give us in terms of the light involved. So we're going to use E equals HF, just like in the photoelectric effect. We know that E is 2.5 times 10 to the minus 19 joules. We know that H is 6.63 times 10 to the minus 34. And there's F, so F is 2.5 times 10 to the minus 19 divided by 6.63 times 10 to the minus 34. Oops, sorry, I was out of view there. I'm sure you'd have coped. Fraction button again, 2.5. Okay, and that gives us a frequency of 3.77 times 10 to the 14 hertz. The information I've supplied was to two significant figures, so the answer is 3.8 times 10 to the 14 hertz. Okay, the next thing that we're going to do, well, you're going to do, is I'm going to ask you to find two things. I want to know what frequency of radiation would be produced by the transition n equals 3 to n equals 2. So I want you to find the frequency. And then I want you to find, and I'm going to change colour pen to emphasise the difference, the wavelength of the light given out when we move from n equals 2 to n equals 1. So I'm going to pause the video there. When you've completed it, no, you pause the video. You're pausing, no cheating. Get on with that. You should definitely be able to do the first one. If you're really stuck on the second one, then you might want to think about E equals HC over lambda. But now you've got to do it on your own. Just going to grab another sheet of paper. So the top one is relatively straightforward because it's just a rehash of what we've already done. The difference between 3.5 and 2.5 is 1. So we've got 10 to the minus 19 joules equals 6.63 times 10 to the minus 34 times F. F is 10 to the minus 19 over 6.63 times 10 to the minus 34. Let's fraction button. Okay, so okay, and that gives us a frequency of 1.5 times 10 to the 14 hertz. So if you got that right, give yourself a big tick. Really well done. Excellent work. What about the other question? Well, you could start with what we've just done and do E equals HF. And then you could do C equals F lambda to convert a frequency into a wavelength. What I'm going to do, because I want to push you a little bit, is to use E equals HC over lambda. This time I'm going to rearrange algebraically. Lambda is HC over E. So it's 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by the energy. What's the energy? The difference between 3.5 and 5 is 1.5 times 10 to the minus 19. Of course, if you need to do that subtraction on your calculator, that's absolutely fine. Kind of my job to be able to do these things really well, isn't it, I suppose? And sometimes I can, sometimes I can't. Okay, so we've got 13,260 for the wavelength, which looks utterly ridiculous. So you can see that's one of those things, it's quite useful to keep a check. That should be a 3 there, shouldn't it? Okay, so that now gives us 1326. So that's 1326 times 10 to the minus 6 meters. Now, personally, see, I'm quite used to dealing with these numbers, and I find that quite confusing. First of all, I'm just going to round it, 1.3 times 10 to the minus 6 meters. But I want to put it in nanometers. It'll make more sense to me in nanometers, even if it doesn't to you. All right, 1,300 nanometers. Well, we said visible light was 700 nanometers to 350 to 400 nanometers. So we're now well into the infrared part of the spectrum. Hope you found that useful.